on how it's made. Paper fans. Walnut oil. And copper. The oldest existing Chinese fans, made of woven bamboo, date to the 2nd century BC. The folding fan was invented in Japan between the 6th and 9th century. Fans were typically made of paper or silk, and famous artists were often commissioned to paint them. The traditional Asian fan, an object of beauty with a practical purpose. The structure is comprised of bamboo sticks, called ribs. The paper surface is called the leaf. In this fan workshop in northern Thailand, they begin with narrow poles of locally harvested bamboo. With a sharp knife, workers cut them to the approximate length of the ribs, then split them down the middle. Using traditional blades, they shave each bamboo strip to the shape of a rib. Ribs are typically about 2 millimeters thick and perfectly flat, so that they can smoothly slide on top of one another. Workers drill a hole in each rib, 6 to 9 centimeters above the base, depending on the fan size. Then they assemble the ribs on a bolt. The number of ribs and their length are what determine a fan's size. The 2 ribs on the extremities are wider and thicker than the others and are rounded on the outside. These are called thumb guards because you flick your thumb on them to open the fan, and they guard the ribs in between from damage. To make the leaf, they begin by spreading the ribs, spacing them out evenly. They lay this onto white cotton and cut out the semicircular shape of the leaf, with the fabric extending 4 to 6 centimeters beyond the rib tips. This fabric will be the leaf's structural backing, giving the paper rigidity and strength. They make that paper just as their ancestors did, mixing the fibrous bark of the mulberry tree with natural dyes. The marigold flower for yellow, for example, or, as we see here, the root of the madder plant for vibrant red. They mix the dye stuff with the mulberry bark fibers, then gather a thin layer of dyed fibers onto a rectangular mesh screen. They keep repeating this process, adding layers, until they build up the paper thickness they need. Then they let the fibers dry in the sun into a finished sheet of paper. When the paper's ready, they cut a piece to match the shape of the cotton backing and iron them together. The 2 layers naturally adhere to each other thanks to the paper's moisture, and a compound in its fibers called lignin acts as a natural glue. They fold the leaf in half and trace a template in the shape of the lower section of the fan, where no paper is required. Then they cut this part off. They brush homemade glue made with white flour onto the parts of the ribs that will be in contact with the leaf. They lay the ribs on the paper and, with an upward sweeping motion, press them down, at the same time wiping away the excess glue. Next, they trim the leaf, leaving about 2 centimeters beyond the tips of the ribs. They glue the edge and fold it back over the ribs. Then they trim the edges along the thumb guards. Now for the most delicate step of the entire process, folding the fan for the first time. Each fold is permanent and will give the fan its form, both open and closed. So precision is everything. Now the fully constructed fan is ready for decoration with water-based acrylic paints. Sometimes the customer requests a certain theme or scene, but usually it's left to the artist's creativity. The artist can manipulate the paints to produce a range of effects, modifying with acrylic gels, media, or pastes to create the bold effect of oil paint, and diluting with water to varying degrees to create a transparent effect, much like watercolors. The final touch is what's known as piping, paint applied through a cone-shaped tip to produce a raised line. This highlights the artwork with raised details. The paint becomes water-resistant once dry, protecting the artwork from damage, and ensuring this Asian objet d'art will always be simply fantastic. Walnut oil has a distinctive, mild, nutty flavor and aroma. It's also nutritious because it's high in omega-3 fatty acids, which are crucial for brain function, reduce inflammation, and may even help lower the risk of heart disease, arthritis, and other chronic conditions. Walnut oil is sometimes used for sautéing, but it's more often consumed cold, typically in salad dressings. Walnut oil produced for non-culinary purposes goes through a refining process, which removes the flavor. Walnut oil produced for gastronomy is unrefined, so it retains its nutty taste and scent. Walnut oil has one ingredient, and one ingredient only: English walnuts. The oil factory buys them from the supplier already shelled. Production methods are much the same as they were 150 years ago. The first step is to shovel the walnuts into a grinder. The grinder pulverizes this combination of full kernels and broken pieces until everything's fairly uniform, roughly 3 millimeters in size. Next step, roasting. Workers pour the ground walnuts into a cast iron kettle on a gas burner. For 30 minutes or so, a rotating arm continuously stirs them to ensure they roast evenly. Roasting enhances both the flavor and aroma. The shelled walnuts have gone from large pieces to ground pieces to roasted pieces. Now they're ready to have the oil squeezed out of them. This cast iron expeller press dates back to the early 1900s. Workers line the bottom with a mat made of natural fibers. This will prevent the walnuts from leaking out under pressure. After loading the press with the walnuts, they close it up and set the press in position. Then they release the piston. It descends and applies 200 kilograms of pressure per square centimeter, crushing the walnuts and expelling the oil in the process. The oil exits the press through small slots around the perimeter, flows down to a trough, which channels it to a spout, which pours it into a collection vat. 2 kilograms of nuts yield 1 liter of oil. What's left in the press is walnut meal. It's used by pastry chefs to add a nutty crunch to cakes. It's also sold to farmers who use it for cattle feed. The extracted oil, meanwhile, moves on to the last phase of the process: filtration. The filter press is comprised of 16 grooved plates made of food-safe plastic, with paper filters in between. Workers compress the plates and filters, then start up a powerful pump, which forces the walnut oil from one end of the press to the other. Along the way, the filters trap all the minuscule particles of walnut, wax, and other natural materials, clarifying the oil. This process takes a few hours, at the end of which the once cloudy oil is clear. Packaging walnut oil in clear glass bottles would look appetizing, but would actually shorten the product's shelf life. That's because walnut oil is rich in omega-3 fatty acids, which, while good for you, are sensitive to light. Therefore, walnut oil is traditionally bottled in tin. After the automatic equipment fills the tin container, workers loosely apply a snap-on cap, which the next machine presses into position. Last stop, labeling. As the tin spins, the machine wraps it in an adhesive-backed label, neatly aligning the label's seam with the welded seam on the tin. Now the oil's ready to drizzle a rich walnut taste onto your pasta, grilled meat or fish, or salad. Humans have been making things out of copper longer than any other metal. Archaeological digs around the world have unearthed copper vessels, tools, weapons, and jewelry dating back at least 10,000 years. Fast forward to today, and copper is one mineral we still really dig. Peel back the layers of modern civilization, and there's a lot of copper. It's used for electrical motors and wiring, high-tech gadgetry, and plumbing. The metal known chemically as Cu is essential to modern living. Pure copper is rarely found in nature. It usually occurs with other elements like iron and sulfur. To mine the copper-bearing rock, a huge drill chews into this Arizona terrain. It drills around 130 holes at least 15 meters down. A truck pumps explosives into them. It's a powerful mix of ammonium nitrate and fuel oil. A mine worker lowers electronic detonating devices into each of the 130 holes. From a safe distance away, he activates the detonators, staging the explosions milliseconds apart. It's an explosion sequence designed to fracture as much of the copper-bearing rock as possible. Shovels scoop up the blasted rock, lifting 50 to 80 tons in one bite. The rock is less than 0.5% copper. Freeing the copper from it involves different techniques. The technique depends on whether the ore is iron oxide-based or sulfide-based. To process copper from oxide ore, they pile the rock in specially prepared leaching areas. They irrigate the rock with a diluted sulfuric acid solution. Over months, the solution percolates down and dissolves the copper. The copper solution drains into a pond. A pump transfers this solution to the plant. In this channel, the copper solution binds with an organic agent and floats to the top. They add an acidic solution, which increases the concentration of the copper and makes it electrically conductive. They transfer the copper solution to a series of tanks that contain starter sheets of pure copper called cathodes. They pass an electrical current through the tank, and the copper migrates to the cathodes. At the outset, the cathodes are wafer thin, but over a period of 10 days, they thicken substantially. They're now 2.5 centimeters thick. Each one weighs about 125 kilograms. The purity is now 99.99%. That's important if the copper is to be processed into electrical products. Freeing copper from the sulfide rock is more difficult. It starts in a massive tumbler called a sag mill. Inside, steel grinding balls smash wet rock to pieces. Exiting the mill, the smashed rock travels over a perforated conveyor to screen out smaller pebble-sized rocks. These smaller rocks continue on to different grinding mills. The larger rocks circle back to the sag mill for another round. Once all the rock has been sufficiently ground, they add chemicals, which coat the copper particles and mix in a frothing substance. The slurry flows into flotation tanks. Air blasts create bubbles that the chemically coated copper minerals attach to. The bubbles carry the minerals to the top of the tank and they overflow. After filtering the overflow, they have a concentrate that's now 25 to 30% copper. They transfer the concentrate by rail to a smelter facility. Here it goes into several large beds. Each one is the size of 2 basketball courts. They add silica sand, creating a layer cake of sand and copper concentrate. The silica sand is known as a flux. It will serve as a purifying agent as the concentrate is smelted. In the intense heat of the furnace, the silica sand melts to form a slag that absorbs the iron and other unwanted minerals. The slag floats up and the copper sinks. Its purity is now 60%. Then it's into a second furnace, where they up the copper content to 98%. Coming up, there's much more to the story of copper. There are networks of copper in the walls of modern buildings, wires and pipes that supply utilities and keep the household humming. Hidden behind drywall, it's easy to overlook the contribution of this thermally and electrically conductive metal. But behind the scenes, copper is a big player. With the copper now extracted from the ore, they pour the residue onto a heap. This molten slag flows down like lava from a volcano. As it cools, it becomes part of the landscape. Meanwhile, in the smelter, a crane delivers the fiery liquid copper into another furnace for further purification. Inside this furnace, the purity level increases from 98% to 99.4%. The molten copper flows out of the furnace and into rotating molds. The molds shape the copper into big rectangular slabs called anodes. The slabs will serve as positively charged electrodes in the electro-refining process that's still to come. That process will take the purity level up one last notch. The copper begins to cool in the molds. A sprayer douses them with water to speed the cooling process, and the copper hardens into the anode shape. A hydraulic cylinder pops them out of the molds. Then a carrier system retrieves them and takes them for a rinse. This gets rid of any traces of a non-stick substance applied to the molds earlier for easy release of the copper slabs. Hooks formed during the molding make it easy to rack up the slabs for shipment to a Texas refinery, hundreds of kilometers away. At the refinery, the copper slabs shed any lingering impurities in this tank as an electrical current is applied. The current causes the copper to gravitate to thin starter sheets. The impurities fall to the bottom. The copper deposited on the starter sheets is 99.99% pure, the purity level required by wire manufacturers. They load it into a furnace that's essentially a tall shaft. Midway down, the pure copper melts and flows to the bottom of the furnace. From there, they transfer it to an insulated metal channel, which keeps it molten as it now travels into a vertical mold. This mold shapes it into rectangular forms known as copper cakes. Copper cakes are used for manufacturing things like copper sheeting and plumbing parts. Fresh from the mold, the copper cakes are roughly 6 meters long. A conveyor serves them up to a circular saw that slices them to lengths required by the customer. Stacked and labeled, this pure copper cake is now ready to ship to the manufacturer. They also process pure copper into rods, a form more suitable for manufacturing electrical wiring. Molten copper moves through an opening in a mold, and, cooled by water, the copper forms a continuous rectangular bar. These grooved rollers will now take it from rectangular to round and reduce the diameter substantially. As the copper travels through the grooves, it becomes an 8 millimeter thick copper rod. The rod exits, and the machine loops it into coils. They land neatly onto a steel spool. Machinery compresses the copper coil, squeezing it down so it will take up less space when it's transported. There's one last squeeze from an overhead press. And an employee ties the tightly coiled copper with extra strong plastic banding. From the Earth's crust to the factory floor, it's been quite a journey. Shipped to manufacturers, it will now be drawn into electrical wiring, and the future is sure to be high voltage.